Let me see. Are we live? Oh, hell yeah! All right, what's up, everyone? Today we will be looking at some journals. I have to pick up I gotta sign a few journals for literature review, so I have to look at papers and stuff and find a couple and read them extensively. So today, the few minutes we have, we'll be doing this. We'll be doing that. Alright, let's see. We've got nature science, nature catalysis, and chemical catalysis. Now, why am I getting catalysis papers when I'm usually doing computational stuff? I honestly do not know. But whatever. We will find something. A nature science. Reject optional cookies, obviously. Explore content. Let's see. I wonder if I'm signed. Do I have an account with them? Alright, let's come here. Subjects, physical sciences. That's crazy, there's no catalysis yet. Let me see. NatCatal. Nature.com/NatCatal. Alright, featured review article, perspective. Molecular scale interactions in heterogeneous photoelectric catalysis. I am not doing any photoelectric catalysis. I am doing metallocatalysis. So let's see. Let's see. Neutral photo generated N-centered radicals as a general catalytic direct hydrogen atom transfer platform for aliphatic CH functionalization. Let's see. So direct hydrogen atom transfer, DHAT, for sp3H functionalization, which is just simply bonded hydrogens. Obviously, they can only be singly bonded, but like on a carbon that's entirely singly bonded. Alright, with a saturated carbon. Classically relies on O-centered catalysis. So direct hydrogen transfer on a saturated carbon typically relies on O-centered photocatalyst. What is an O-centered photocatalyst? Let me see. What is an O-centered let's see. O-centered photocatalyst. An O-centered photocatalyst refers to a class of catalytic materials in which the primary oxidative or active species is an open shell organic radical localized on an oxygen atom, OCOR. So a class of catalytic materials in which the primary oxidative or active species is a radical localized on an oxygen atom. So are you saying like CH2O? CH2O. What do you call it? O-centered. No. No, not CH2O as in double bonded. It literally just means that. Oh my gosh. Okay, it makes sense. Let's see. In which the primary oxidative active species is an open shell organic radical localized on an oxygen atom. So that equals like our alkyl groups on our oxygen atom on our carboxy group. Okay, so these catalysts such as specific carbazole, anthraquinone, or polyoxometallic derivatives are driven by light energy to generate transient oxygen-centered radicals that actively participate in chemical reactions, such as the degradation of pollutants or the production of hydrogen peroxide. Right. So these catalysts are driven by light, okay, to generate transient oxygen-centered radicals. Okay. So basically, what I'm saying here is, let me see. When these molecules interact with light, the alkoxy groups break off, or hydroxyl/alkoxy peroxy groups break off. Right? Let me see. How many center groups did they mention here? Hydroxy radicals, okay, and peroxy radicals. Yeah, it makes sense. Peroxyl radicals. Okay, what's this paper here saying again? It says that direct hydrogen transfer is classically relies on O-standard photocatalysts, and now we know that O-standard photocatalysts are really, at least based on the quick summary we have seen, or probably there's more information I need to understand to get that, are catalysts that when they interact with light, break off to form either like a hydroxyl radical or an alkoxy radical or peroxyl radical, where hydroxyl is more like, let me see, so like I'm guessing like, actually no, a hydroxyl, I mean, it's like O H, and then you have 1, 2, 3, 4 normally, and then you have this negative. Then alkoxy could be like OCH3, right? And then same thing. And then a peroxyl is probably, like, I mean, a peroxyl definitely has to be like this, but like instead of just CH3, you have C double bond O, and then you have H, and then you have like this. Alright, put the lone pairs and stuff. So that definitely has to be it. Definitely has to be it. Okay, alright, so classically relies O-standard photocatalysts. Now, neutral N-centered acridine photocatalysts have been added to the toolbox, enabling mild, scalable, direct hydrogen atom transfer that is compatible with a broad substrate scope and transition metal catalysis. See, because like I'm not trying to do anything that's not open. I mean, why would in nature, you gotta step up your game, but I'm not trying to do something that's not open access, man. Because this is my computer. I'm not trying to log into my stuff right now. Alright, let's see. Do I want to do this? I mean, this sounds cool. I mean, I definitely could learn a lot, but is it related to like the research I'm doing? Probably not, honestly. Like, I know this is catalysis and stuff, but it's not the kind of catalysis I'm doing. I'm not doing any photo catalysis, so it's a no for me. I'm gonna pass on this guy. pH dependent stabilization and interface coupling of palladium species during alcohol oxidation. Right? Okay. So metal dissolution is a common cause for catalyst deactivation in heterogeneous catalysis. So A couple of things. What is catalyst deactivation and what is metal dissolution? And you can ask Google, what is catalyst deactivation? As a gradual or sometimes rapid loss of a catalyst's ability to drive a chemical reaction. Oh, wait! I thought. Oh wait, okay. You know what? This so. Huh. How does the activation is an area for substance effect? I don't care about what. I mean, love you guys, but all right. I mean, I just need like a quick summary, so I'll stick with this for now, and then do further study later. All right, okay. My catalyst naturally decay over hours, expanding depending on the application. So I mean, okay, that's a rough, very very rough overview. Um, well, and what is metal dissolution? Uh, Metal dissolution is the chemical electrochemical process where a solid metal is oxidized and enters a liquid solution as free floating ions. So, if we're to just apply what we've seen so far, right? Metal dissolution, which is when the metal gets oxidized and turns into a free floating ion, is a common cause for catalyst deactivation, aka when a catalyst is slowly being reduced in its catalytic activity over time, over a period of years, right? Let me see. Okay. Now, after mapping palladium speciation as a function of pH, which I would assume to be the kind of oxidative states palladium could take up, uh, regarding the pH, right? I'm gonna search this up. So, a cooperative enhancement mechanism has been between separated gold slash carbon and palladium carbon catalysts and evolving solid dissolved palladium species is identified for alcohol oxidation. I'm not that terribly interested in this, honestly. Um, let's see. Like, is catalysis I mean, is catalysis something I really want to do? Like, let me see. I don't think it's something like I would want. I mean, I would want to do that much, right? Like, why did I get catalysis, bro? I mean, I guess we'll see. We'll see. I mean, I guess this one really made sense to me. Came out yesterday. Let's see. Selective carbon-carbon bond cleavage enables annulation between beta lactams and pi systems in nickel aluminum bimetallic catalysis. Selective carbon-carbon bond activation adjacent to heteroatoms is challenging due to competing carbon X cleavage, right? Alright, what is selective carbon-carbon bond activation? I mean, I like... So selective carbon-carbon bond makes a little bit of sense, but the activation part is what is missing in my mental framework, right? So what is selective activation? Did they say bond activation? Because that could be totally different. Let's see. Bond activation, yes. Okay, selective carbon bond activation is a synthetic technique in organic chemistry that uses catalysts like transition metals to selectively break specific carbon-carbon bonds in a complex molecule. Okay, so I mean, so if to take that and give an example, it could be maybe the use of, say, nickel, because nickel's or zinc, which is like a common catalyst too, right? To split this bond or to cleave this bond, creating like freestanding, well, not freestanding, but creating what would you call this, right? Like, what's the results of the cleavage? We're just gonna call them cleaved compounds. Maybe I feel like there's a more representative word for that. Alright, okay, so selective carbon bond activation, which is the use of metal ion to break these carbon bond adjacent to heteroatoms. Now, what is a heteroatom? Any atom in a molecule that is not carbon or hydrogen. Oh, okay. So, organic compounds, carbon, hydrogen, oxygen, nitrogen. Right, just right off the bat. So, if let's say they're referring to like oxygen and nitrogen. What they're saying here is, so using a metal to cleave these carbon-carbon bonds, when each of the carbon bonds have either an oxygen or nitrogen or both, it's challenging due to competing carbon/X cleavage. So I'm guessing that the same cleavage, what would you call it? Cleavage that you would get with a metal when you try to apply it to like a bond. Okay, let me rephrase my word because I need to be more concise and more direct with my language, right? So, cleaving a carbon-carbon bond that has an oxygen and nitrogen on it is difficult because there's also a race to cleave like carbon to nitrogen/oxygen bond on that same carbon on that same molecule, right? So let's say there was like let's come here, right? So let's say we have like C, and then you have like OH or something, right there, whatever, and then we have like NH2, right? And you have like nickel, whatever. So apparently cleaving this bond is harder because this also wants to cleave this guy too, or like so it's harder, right? Compared to like if it was something like this, C H H, and then like another C something, like C something, right? Right, whatever. I'm just using this to represent like whatever possible R groups because I don't care. So apparently cleaving this when like we have one of these on it is harder than cleaving this, right? But I mean, because it's steep and it's because of what, steric hindrance. This work develops a nickel-aluminum catalytic system that enables precise activation of the inert C2C3 bonds in beta lactams. Facilitating efficient annulations with pi systems. With pi systems. Oh wait, come on, bro. Alright, I'm just gonna go. Yep. What other journal did I get? Like Nature, Science, Nature Catalysis, Bio. I think I'm gonna take a look at biomacromolecules because that sounds cool. And it sounds. I mean, even though yes, I am doing some catalysis work right now. I am working with peptides, and I think biomacromolecules would be a better journal to look regarding to how it relates to my current field of research. Also, actually, so but since the size of peptides I work with, I mean, okay, let me know. I mean, they're pretty short. So I wonder how large this would. How many components would a molecule have to be a macromolecule? Because proteins you could say they're macromolecules. I mean, they're definitely molecules. They're macromolecules with their own like systems and everything. Same thing with peptides. I feel like, and I know I read somewhere that like the cutoff for something to be a peptide is like um 50 residues. So like if you have something like 51 residues, boom, I mean protein terror. I mean I feel like it has to be plus or minus something, right? Like let's say 60 residues, you're now protein. Let's say 60 residues, you're now a protein. I think. Okay, so where were we? Oh, it's not even open access. What the hell am I doing? Oh my god, bro. Okay. Actually, let me see. What? How many molecular components would a molecule need to have to be considered macro? There's no exact thing. Okay. No, I don't trust this summary at all. The specific one, but whatever. Okay. So beta lactams. Oh yeah. What is a beta? A space of a chemical ring structure that serves as a core foundation for. Is this cycloamine ring? Huh. Okay. All right. Let's see. Facebook develops a nickel aluminum catalytic system that enables precise activation of the inert C2-C3 bonds in beta lactams, facilitating different efficient annulations with pi systems with high regio control. So pi conjugated systems, rich in what you call it, double bonds, right? Alright, so C1, C2, C3. So these carbons. So basically, oh, okay, I see. Because this is like a heteroatom. Oh, of course. Sulfur is a heteroatom. Nitrogen is a heteroatom. So okay. That's cool. So this work develops a nickel aluminum catalytic system that enables precise activation of the inner C2C3 bonds in beta lactams, facilitating efficient annulations with pi systems with high regio control. Alright, so activation, which I would assume to be bond breaking by metal. Boom, boom. Cleave this bond. Cleaving that bond. I don't care. Alright, selective carbon bond activation between two heteroatoms, aka nickel, nitrogen, sulfur. It's challenging due to competing carbon X cleavage. So basically, if you want to bring a metal to cleave this bond, you also risk cleaving this bond or this bond. So this group risks being broken off, right? Metal. If you try to use the metal to activate it. This work develops a nickel aluminum catalytic system that enables precise activation of the inner C2C3 bond in beta lactams, facilitating efficient annulations with pi systems with high regio control. This actually seems pretty interesting. Can I see the image real quick? Hold on. Yep, C. Wait, what? Why is this C2? I mean, wait. Did I just mess up my C1? C2? C1 has a nitrogen. Is this specific? Wait. Pause. You know what? You know what? Let's see. It's 8:10. I'll give this shit 5 minutes. Alright. I'm gonna go over the biomicromolecules. Actually, can I go over the biomicromolecules? ECS Biomicromolecules Journal. Okay. Oof. God, like I saw programming and my mind was like, oh, okay. Let's go. So code. Speaking of code, here's mine. Oh, by the way, the Hindley Miller type checker. I mean, it's coming up a bit nicely. I think what I have to do is find a way. I'm trying to think. Should type annotations exist in the AST of a function declaration? It kind of makes sense, right? Because you have an identifier with an annotated type, and basically, if you really think about it, what do you call it? A parameter in a function declaration. It's kind of like it's like a let binding, but scoped to just the parameter, to the list of parameters, right? Just scoped to that function. They are the default let bindings within that function, right? And then I also read that since you would need to do register allocation and things like that when you eventually do code lowering into IR, you kind of do need to. I mean, you shouldn't store the parameters as separate entities. But honestly, I felt like conceptually, it would be kind of nice to separate them. But the more I think about it, they're kind of just like let bindings, but to the functions, right? So I'm thinking of changing that. Instead, we will come in here and oh, this is not even the right. Let's see. We'll come up here. Alright. I don't know how to reload this thing. Core source. No. section of it. User nodes expert. Yeah, we got a func param. You see, like I'm putting the func. I'm putting the func params in the nodes. But then again, so like I'm thinking, right? We should low key have the type instead of being like a token. We should have it be like a type pointer. But then that risks so what was the trade-off here? Like if we do this, it means we have to like construct like a type at parse time, which for like an untyped AST, I don't think that's the right move, right? Because normally, like when and also like the stupid thing is like I forgot to put like annotations for like I forgot to like type. It's a good place to store like type parameters for the let bindings and const bindings too, which is ridiculous because we need it for type inference. Okay, so like oh yeah, client D, boy, please. Client D, 127 errors is insane, my brother. Oh shit, no, never mind. I'm trying to find one that has like let's see, like did we do like that's okay, let's go to parse. Function. Yeah. Let's just like actually I don't want to change anything here because I'm still working on my computer. Alright, let's do function params. Alright, so we're in this loop. If it doesn't match this, break, right? If param type, we make this optional and it's gonna return a token. Wait, what? Yeah. Optional returns a stored optional token, right? And then what we do is, give me 1 second. Yeah, no, I'm gonna fix all this later. Because I changed a bunch of stuff. Oh my gosh, holy sidetrack. But anyway, 8:16. I'm already out of time here. Okay, whatever. I guess we can just like take a look at biomicromolecules later. But honestly, I'm thinking of, let's see. So even though like I say I'm not really trying to do catalysis like that, I mean I still think it's good that I know a bit of catalysis. I read something from the catalysis journal, a subsection of the Nature journal, of Nature publication, right? I think this is good. I also think this is good. Is it because like they're more familiar to me? No, but I think like I took my time to really understand this, and I guess it makes sense to want to read these if the goal is to learn about catalysis and not really find something. Yes, find something interesting, but how would I define interesting? Well, interesting is something I'm most like I am familiar with enough to want to know more. That felt like tautology. I'm not even gonna hold you. It does, but the point is, it does feel interesting, even though this is not open access. Let's see. This looks good. This looks good. So out of these two, I'll take them. I'll take these two. So I'm gonna write them down somewhere. Where's my notebook? Notes. I'm gonna write it on this biotage. paper. So bio, so from Nat for nature catalysis. Let's see. Neutral photo generated and centered radicals as a general catalytic direct hydrogen transfer platform for aliphatic CH functionalization. It is so insane how, like, just reading this, you would think it's something that sounds too complex, but once you have the, I guess, bit of insider knowledge that you get from, like, a chemistry degree or biochemistry degree, or just sufficiently studying chemistry if you, like, study on your own, well, it seems like it sounds pretty simple, right? And it doesn't sound as complex. The demystification of the unknown, guys. That's why you have to go to school. That's why you have to study, because otherwise things sound stupid and complex, and then it feels like science is being gate kept. Which is also one problem I have with, like, people saying that science is being gate kept when they use fancy terminology like this. No, you need to understand that science is a compounding field, right? So if you're in the game, it's expected you have some basic knowledge of what the field does, and specific basic knowledge on specific concepts in that field, so that when you then see what people are doing in that field using those basic concepts to create, like, to create new knowledge, it doesn't sound mysterious to you because you already know. A lot of people come out and say, oh, this paper sounds so complex, science is being gatekept. No, you just don't have the preliminary knowledge to understand what these individual bits and pieces mean, to then give you that, like, the glimmer of, to then give you that like, understanding that, to look at the topic of the paper and be like, okay, this is what it's talking about. All right, so I'm also gonna do selective. I think I'm more like, does beta lactam seem like something that I should have known about? So I think I might just do that. But either way, CC bond cleavage enabled annulation between beta lactam and pi systems via nickel aluminum bimetallic catalysis. Boom. Alright, so even though I wasn't even going to buy macromolecules, let me see, what's it good for it again? Oh shit, oh wait, I zoomed too far out. Oh my god, I'm lost. I'm officially lost. Wait, no, stop this. Oh my gosh, I'm lost. I'm literally lost. You fell asleep, host. I'm lost. Oh my god. Okay, officially lost, guys. Let me see. I gotta do this Thursday. Oh, there you are. Let's see. Bruh. Okay, whatever. We'll find it. We'll find it. This is something for another time. But alright, y'all. Peace out. And see you some other time. How about that? Alright.